Uh, Good morning, everyone. Today, we are going to discuss superconductivity and its technological applications. We will begin with the concept superconductivity and its technological applications. So, before begin with the superconducting phenomenon, we should understand something related to normal conductivity. So we know that in daily today life we are using copper as a good conductor for heat and electricity. So because the copper is a cheap and affordable material compared to other good conducting materials such as silver, gold and platinum. So these silver, gold and platinum are very good conductor than the copper. Copper is comparatively less conducting than these gold, silver, and platinum, etc. But uh, in any electronic devices as well as the any electronic equipment and home appliances, we are preferably using copper material for electrical purpose. So we need to understand what is superconductivity. In order to understand the superconductivity, we should know something about normal conducting phenomenon. So superconductivity, the phenomenon in which the phenomenon in which the electrical resistivity of the resistivity of the material suddenly drops to suddenly drops to zero, or we can say it suddenly approaches to zero at temperature less than critical temperature critical temperature. So what is here the critical temperature? The critical temperature is the temperature at which the normal conductors become superconductors. Means in superconductors, the critical temperature is the transition temperature when the temperature of the system, that is T, which is equal to Tc, or the T less than Tc. For this condition, the material behaves like a superconductors. Whereas the condition temperature greater than Tc, or the temperature T which is not equal to Tc, then the materials becomes normal conductors. Normal conductors. And if you plot a variation of electrical resistivity as a function of temperature, this is the temperature axis. So this is the resistivity axis. See, this is the transition temperature I'm here. This is T which is equal to Tc. So above this the material above this temperature, the material shows a large electrical resistivity. So when you cool down this material to the lowering temperature or cooling temperature, the electrical resistivity of the materials abruptly dropped and reaches to zero here. So above this region is a normal conductor, and below this region is a superconducting state. Superconducting state. So the temperature less than critical temperature, the material behaves like a superconducting state. Temperature greater than critical temperature, the material becomes a normal conducting state. So now we need to understand here why this the electrical resistivity is abruptly dropped to zero. So try to understand here. This is an entirely an abstract idea of getting the electrical resistivity of the material suddenly dropped to zero. See, this is a pure. This is an abstract idea. We are not getting why what happened inside the material. What is the quantum mechanical behavior happening within the superconducting materials? We don't know. Still, we don't know. But later on stages, the development of superconducting hypothesis and their discoveries. So the detailed quantum mechanical description um is proposed by Burdeen, Cooper, and Schrieffer. That is the microscopic description of superconductivity. So then we came to know that why these electrical resistivity is going to be zero or abruptly drop to zero. We will get a clear idea in the BCS theory. So later on stage, we will see that why this BCS theory is more important for the materials. Okay, now next here the phenomenon of this superconducting state was first discovered by a Dutch physicist Helijk Helijk Heik Kemmerlinks Ones in 1911 at Leiden. Leiden. So he took a capillary of a mercury. He done the experiment on mercury in a capillary sitting on sitting on a cooling bath. Cooling bath. Cooling bath. So after this after this invention, there are many innovations have done on superconducting phenomenon. So over the 70 years, there are many Nobel Prize also received on this superconducting phenomenon. Over the 70 years, there are number of Nobel Prize we have received. So next is we need to understand the difference between what is the mechanism happening in the normal conductors and superconductors. So normal conductors and superconductors. Conductors. So we know that the free electron theory, that is Drude Lorentz free electron theory of materials, that is the classical free electron theory, we can say. So here in the classical free electron theory, uh, the solid having more number of free electrons, these free electrons are randomly moving throughout the solid, and they are very free because the potential energy of the system is completely zero, so that these electrons are moving throughout the solid. So if you consider the net velocity of the system is going to be zero, of course, the net velocity is zero. For example, if you consider a solid, this is imagine this is a three-dimensional solid, you can say. So these solids consists of an Avogadro number of atoms. You have n number of atoms. I am simply taking copper an example. Copper. So these are the number of atoms are present in the system in a solid. So each atom having one free electrons. So that is because copper is the atomic number is 29. If you write the electronic configuration of copper, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. So that is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. So this you can count the value 4, 10, 18, 28, 29. So one valence electrons is moving all copper atom having one valence electrons. So these valence electrons are moving randomly throughout the system because the system is completely present in the absence of electric field. So the electric field you are going to give 0 when there is no electric field. So these electrons are the atoms are electrically neutral because the center of gravity of positive charge and center of gravity of negative charge, they are balanced. The net neutrality of the system is going to be 0. The atoms is electrically neutral. So these electrons, they are moving in a random orientation. So if you consider the velocity of each individual particle, so this electron as velocity is some around uh, less than this electron, this electron, this electron. Means it's a random orientation, or we can say the Brownian motion. The net velocity of the system is going to be zero. Of course, we know that uh, current, that is, the current is depends on the number of atoms or the density of electrons, the charge of electrons, and also the drift velocity and also area of the system. The current is dependent on these, the number of atoms or the density of electrons and the charge of electrons and the drift velocity of the electrons as well as the area. But if you consider individual velocity of these electrons, so the net velocity is of course zero because this electron is going to be this direction and it is moving back and it is going this way, this way. So if you consider the net velocity of the particle or net velocity of an electron, of course it's going to be zero. So that Vd is equal to zero. So if you consider the current, definitely it's going to be zero. When this in the absence of electric field, electric field is going to be zero. Then what happened if you apply some positive potential? Instead of zero, you can put some 2 volt or 3 volt voltage to the system. What happened? So these electrons having negatively charged particles, when we are applying the electric field, that is a positive potential, we can say E, which is equal to EV potential. It is something called, we can say the F is equal to E, which is equal to EV. So because this is the driving force, so these electrons are taking an kinetic energy, and these electrons are moving opposite to the direction of applied field strength. So if you are applying the field, so the electrons are, whatever the electrons is present in the solid, they are moving in constant velocity like this. They take an kinetic energy, and these electrons are carrying some energy in the form of current. So the net velocity of the system is valid, and you will get some velocity of the individual electrons. So you will expect the net velocity. Of course, you will get current. If you have a positive velocity, so that is eta, density of electrons, charge of electrons, vd. So if the velocity of this system is not zero here, because all electrons are taking a kinetic energy, and these electrons have some velocity, so you will expect the current, positive current. Current is positive value. Then now here, these electrons are taking a kinetic energy and constitute a current. So we know that the flow of electrical charges constitute a current. So this is a the phenomenon in the normal conducting process is happening. So most of the materials, we are going to take the copper as a good example. But what happened? The system, the variation of, if you plot a variation of electrical resistivity as a function of temperature for the normal conductors, right? We need to understand that one, and temperature here. See, we have to consider here the three important materials. One is the material, I will take a pure materials. The material is does not contain any impurities, but it's a pure material. You can see the resistivity as a function of temperature here. So I can say this is the pure metals. This is one point. Second one is the material is having certain impurities or interstitials or stacking faults, any other imperfections in the system. So this is, the electrical resistivity is not going to be zero, but there are certain resistivity here. This material shows some resistivity. So we call it as, this is the residual resistivity. So that is, we call it as a rho naught. This is a residual resistivity. But one more important material already discussed, that is the superconducting materials. So the electrical resistivity of the materials is abruptly dropped to zero at temperature T is equal to critical temperature. So this is a pure metal. This is a impure material, impure material, and this one is a superconducting material. Superconducting materials. Okay. Now, again here, why this pure metals are showing the electrical resistivity is completely zero. This is a pure metal. See here, the electrical resistivity is zero at absolute temperature T is equal to 0 Kelvin. Why means, see, if the temperature of the system is going to be absolute 0 Kelvin, if the materials are impure, then definitely there will be no resistance exist within the material, so that the material is showing the 0. But in reality, we won't get a pure crystal, because you can take any kind of material, for example copper, gold, silver, any platinum, any kind of materials. These materials are not pure materials. There are some impurities which is added within the materials. For example, if you take a gold, you won't get 100% pure gold. You can expect 99.9 kdm, like that. There are certain impurities which is exist within the materials, so it's an inherent nature. There are no perfect crystals, so there are no pure materials. So there are some materials, they have certain impurities. But see here, the electrical resistivity is not going to be zero, but there are certain residual resistivity. Why this is, the impure material shows certain resistivity. So this was explained by the Matheson's rule. So that is Matheson's rule. Matheson's rule. So this Matheson's rules, what it says the resistivity of the system, which is equal to rho of t plus rho naught of t. It depends. So what is this? The rho is a function of temperature. Of course, resistivity with varying with respect to temperature. So this rho of t is due to the resistivity is depend on one is this is the temperature. As the temperature increases, the resistivity of the system is increases. So we say rho of t is a phonon contribution. Phonon. Another one is rho naught of t. So what is this rho naught? It's an impurities. Impurities. Or also you can write the rho of t due to phonon plus the rho naught of t due to impurities. Impurities. So the electrical resistivity of the materials is dependent on such parameters. One is the phonon contribution, another one is the impurities. So we will discuss what exactly uh, the electrical resistivity of the system varies. So once we understand this electrical resistivity of normal conductors, then we will compare with the superconducting materials. Why superconducting materials are shows zero electrical resistivity as a function of temperature. So here also we are talking about the electrical resistivity as a function of temperature. And in superconductors also we are going to consider the electrical resistivity of the system is abruptly dropped to zero when the temperature of the system is cooled down to critical temperature. So now this we will discuss. So we are discussing the Matheson's rules now. I already mentioned it's a rho which is equal to rho of t due to phonons plus rho of t is it's an impurities. I already mentioned there are no perfect crystals exist within the system or in the nature. So there are some impurities or interstitials or stacking faults. These are the crystal imperfections are present in the materials. So one thing is I already mentioned the graph which represents the variation of electrical resistivity as a function of temperature. We discussed. So one here the electrical resistivity of the system for a um, impure metals, it's not going to be zero. There are some residual resistivities present here. See, this is the rho naught. Why this has happened? See, the temperature is increases, the temperature of the system is increases, the electrical resistivity is increases. As you bring down the temperature at absolute zero, but the material does not show the zero electrical resistivity, because see, if you consider a solid, for example I'll consider the copper. So you can take a copper material, it does not contain all pure copper atoms. So there are copper atoms, and also there are some other impure materials which is also incorporated within this. I mark it as a shade mark. This is the impure metal, impure atom along with this copper atom. Okay, so these are the impure atom, or you can say any other bad conductor which is while extracting the oring the system or in the blast furnace while you extract the material. So there are some impurity materials is added in the copper materials. So this is one of the reason. One is the impurity. So what about another thing? So there are some vacancies. So all crystals are not perfect crystals. There are some vacancies. So I make an point. This is an this dot is a vacancies. These are all vacancies and impurities and some grain boundaries and stacking faults. So these are the impurities in the crystals. So these are responsible for the electrical resistance. Even for temperature is absolute zero, so these are responsible for residual resistivity of the materials. That is one thing. So second is the uh, resistivity as a function of temperature with phonons. What is this? See, you have to increase the temperature of the system. For example, this is a material. So now these are the atoms, but you have put some battery. So these are atoms. The electrons are moving because of positive potential. So E, which is equal to some positive potential you have supplied to the system. So the free electrons are accelerated. They are moving opposite to the direction of field strength. So there are some electrons, free electrons. They are moving opposite to the direction of field strength. So all electrons are moving and they are participating in conduction process. Okay. Now these electrons are moving, but I do the so the temp. This is a we consider at room temperature. At room temperature, but you increase the temperature of the system. Temperature of the system you are increased. Then what happened? So these lattice ions. So once the electrons are moving here, these are the lattice ions, and we call it as an ion core. So these ions are get start vibrating. So this ion is vibrating, this ion is vibrating, this ion is vibrating. The entire system of lattice ions are going to be vibrate about their mean position. When the temperature is increased, you have to increase the temperature of the system. So due to this reason, due to the vibration of these lattice ions, the electrons are the flow of electrons is disturbed by the lattice ions. The lattice ions are disturbing the electron flow. Of course, these electrons are lesser mass and these positive ions are heavier mass. So these electrons are interacting with ion cores. So what happened here? The electron and ion, lattice ion interaction, or we can say electron phonon interaction, or we can say electron the scattering center, electron and scattering center. So what happened if the electron is lesser mass? So these electrons are interacting with the lattice ion, so they take a random orientation. Again, the velocity of the electron is very random. So what happened? The entire system is going to be thermally agitation. So the material is heated. So then the if the temperature of the system is increases, the electrical resistivity of the material is increases. When the electrical resistivity of the material is increases, then of course the conductivity is going to be decreases. So this is the normal mechanism, general mechanism is happening in the um, normal conductors. So this is a purely classical free electron theory. So that is proposed by uh, Drude model. Drude model. It's purely a classical approach. And there are saying many later the Sommerfeld, one of the pioneer in quantum physicist at the time, he proposed quantum free electron theory. The picture is quite different than the classical free electron theory. There are many drawbacks which is exist in the classical free electron theory. These drawbacks will be overcome by Sommerfeld. Uh, so we will see in the later section the quantum free electron theory. So this is the normal electrical resistivity mechanism is happening in the normal conductors. Let me discuss um, superconducting behavior.